They might keep it for like getting
Oh!
satisfaction.
I'm live. Okay, it worked. I don't know, honestly. Just work here.
Oh yes, why should you know anything? You
Yeah.
just work.
I just work here, bro. You go to Target and go ask the employee, how do they manufacture this coffee pot? You're like, dude, I just work. I don't know how they make everything, right? Okay, why is this true? Let's do the unit circle first. Using some geometry, all right? It's a little weird at first. If you showed this to like a geometry student, they'd probably find it, one, they'd be confused by the radians. But if you put a 90 degrees in there, they'd probably be like, well, wait a second, how are you taking a sine of an angle bigger than 90? That's kind of weird. But anyway, you can look at the unit circle and say, well, consider some angle wherever it would be. Let's say an angle here. Anything. This angle could be any angle. If that's where theta is, where is theta plus pi over 2?
On the other side of the circle? Like the left, top left.
Yeah, you basically would rotate 90 degrees. Does that make sense to everyone? You feel okay about that? So the angle we rotated through to get to this position is theta plus pi over 2, right? So let's compare the sine of this guy, right, to the cosine of this guy. Well, where on here is the cosine? Where's the cosine of theta? It's that distance, right?
Mm-hmm.
So that distance there is the cosine of theta. And where's the sine of theta plus pi over 2? It's this. Does that make sense?
Mm-hmm.
So the sine of theta plus 90 degrees. And so a diagram like this shows pretty clearly that now maybe the real interesting thing would be to notice that these two angles are complementary and these two angles are complementary. So therefore, how big would this angle be right here? It would actually be the same size as that angle. That makes sense?
Mm-hmm.
For example, say this was 20 degrees. If this was 20, then this guy would have to be 70 because 20 plus 70 plus 90 makes the full 180 there. So if this is 20, then this is 70. And if this is 70, then this is 20. It's another right triangle over there. And so you can see, well, this and this would have to be the same exact size because it's the exact same. So anyway, that is a good unit circle explanation of why this has to be true for any x value you pick. Okay, feel okay about that?
Mm-hmm.
You could go into greater depth if you wanted and talk about, well, what happens if theta was, say, like over here to start? Well, then theta plus pi over 2 is going to be over here. Then they'd both be negative. How about the graphs? This is actually kind of the more important part. Is in terms of the graphs, though, what does this graph look like? Cosine graph, can you visualize it?
Yes.
Nice and symmetrical, right?
Yep.
It's an even function, all that good stuff.
Mm-hmm.
How about the sine function? The sine function is the same shape, but it's shifted. So that's the key to understanding this identity graphically is, where is this point right here? Pi over 2, yep. So pi over 2, 1 is a very prominent point on the sine function. So therefore, if you graph sine of x plus pi over 2, this right here, the plus pi over 2, what does that do to the function? Yep. Shifts it left pi over 2 units. Well, if this point shifts left pi over 2 units, where does he live now? on the y-axis, right? And so then lo and behold, look, this graph would be identical to this graph. So. Okay, how do we feel about that? Okay, so for number 12, your answer to that would just be very similar to this one. Your approach is very much the same. And you're just going to basically talk about how, I think in that one, you're talking about shifting the cosine function, right?
Mm-hmm.
So in that question, you're kind of saying, well, if you shift the cosine function to the right, pi/2 units, you'd end up with a graph identical to the sine function. Oakley? Okay. Are we ready, spaghetti, to discuss what these graphs look like? Okay. This guy. Who is his best friend? The cosine function. So this guy, in order to understand this guy, the key to understanding this guy is to understand this guy, which we hopefully do already. So can someone name a point on here that would tell us big information about the behavior of that guy? 0, 1 is a good one. I like that. Yeah. 0, 1. What else? Any x-intercept. Yep. Let's identify this one and then this one. They're both going to be pretty relevant. Where's that first one live?
Pi/2, 0.
Yep. Pi/2. The real key being that x value. And how about this guy? 3pi/2, 0. So let's see. Don't say the answer if you know it. Everyone think about this one. Fill in the blank. Fill in the blank to the sentence. This graph has a 0 at pi/2. Therefore, this guy has a blank. Who knows the answer? What's the answer? Asymptote. Yeah. Everyone understand that? And if you're like, well, why? Well, the why is because this function is the reciprocal, right? So because the cosine of pi/2 is 0, if you plug pi/2 into this function, you get 1/0, which indicates to us that there's going to be an asymptote. Okay, so let's draw that asymptote at pi/2. And do we understand that there would then, by the same exact logic, be one at negative pi/2?
Mm-hmm.
And 3pi/2? And I have barely enough room. I'll give negative 3pi/2. Feel okay about that?
Mm-hmm.
Okay. This point, that tells us that what point lives on this graph?
Which point?
This guy, 0, 1. So therefore, this graph would have the point.
0.
You're thinking of inverses. That will be a thing. Talk about that tomorrow. It's on an inverse cosine. If you had an inverse cosine function, you'd have a swapping of points.
0, 1.
0, 1. Very good. Very good. Right? Because if you plug in 0, right, the secant of 0 is 1. Because 1/1. Cool beans? And so where is this curve going to go? It's going to go up, or it's going to go down? It's got to approach that asymptote. It's going to go up. You might recall that secant values can be bigger than 1 for example, the secant of pi over 6. Oh, easier is pi over 3. The secant of pi over 3 is 2. Above 1? By the way, this dude is an even function, so his reciprocal is also an even function. And so we get the exact same behavior on the left side. Look how happy he is. But you know what's going to happen between pi over 2 and 3 pi over 2, my cosine values are negative.
Upside down.
You'd be getting
So-
sad.
You got a frowny. Likewise over here. It's really nice understanding even and odd functions because you don't have, you get to kind of sort of compartmentalize some knowledge. You don't have to think super duper hard about every single point. You can kind of go, oh, I know the symmetry. So I know the right side and the left side. And then this will just keep going forever, right? Just like a sine cosine function. There we go. We'll go sad, happy, sad, happy, sad, happy, sad, happy, forever and ever. Okay? Good feelies there? Good. Really good feelies. Someone in the other class had a very good comment. We were about to do this one. And it's kind of connected to the thing we just talked about at the beginning of class. Anyone think they know? Kind of summarizes exactly what this is going to look like based on the fact that we just graphed this one.
Are all the asymptotes going to be shifted?
How much?
Half a pi.
Half a pi, exactly, yes, exactly. So it's like, well, isn't the sine graph just the same as the cosine graph, but just shifted to the right slightly? So wouldn't the same thing be true for the reciprocal functions? Yeah. So like, okay, this guy has asymptotes at all these half multiples of pi. So this guy is going to have his asymptotes at all the whole multiples of pi. So for example, and yeah, like it's all going to shift over to the right. So this would be at 0. Is this making sense? Or this guy would happen at pi. So at 0, at pi, at 2 pi, negative pi, and so on and so forth. I'll put one more in. Okay. Between, and then just for clarity here, the cosecant function is just the reciprocal of the sine function. So where does this guy have his asymptotes? Wherever this guy is 0. Where is this guy equal to 0? At all the whole multiples of pi. Between 0 and pi, is this dude going to be positive or negative? Yep, between 0 and pi, all of my sine values are positive, right? And so I get, also, just think of shifting this whole thing, just grabbing it, pulling it to the right, pi over 2 units. You end up with the exact same pattern. Important to note, what are all of these y values? Like, what are these? 1. Yeah. Negative 1, 1. Negative 1, 1. Okay? So you juniors that are taking the quiz, something to think about is the quiz will ask you questions like, what are the coordinates of this point? And you have, and they'll give you the function, of course. But they'll be like, given this function, what's the coordinates of this point? You have to understand two things, which is one, the x value would be 3 pi over 2, halfway between those, and the y value would be negative 1. Okay? And then I'll show you in a second here. What if you throw a multiple out here? What if you make this like a 3? does that do? Well, instead of having the point say pi over 2, 1, it would become pi over 2, 3. All the y values would be multiplied by 3. Okay. Cotangent time. This one might be interesting to you, maybe. Okay. Thinking unit circle-y. Hope we all recall, how do you get the cotangent? So this point had like an x and a y value. That'd be the tangent. Yep. Yeah, so the cotangent is on the unit circle, it's the x to y ratio, x over y. So where is the cotangent going to be 0?
Zero.
Well, let's look at 0 first. Hold on. This one always trips people up, the cotangent. And it's because it's kind of a rare one. What's the tangent of 0? Given that that point has an x of 1 and a y of 0, tangent would be 0. So then what's the cotangent? Undefined. So what structure is cotangent going to have at 0? Asymptote. Very good. And then up here, the tangent of pi over 2 is undefined. So the cotangent of pi over 2 is going to be 0. And then over here at pi, the cotangent of pi is undefined. So my next asymptote is going to be at pi, and then 2 pi. Any questions yet? Anyone? Okay, and we established, hopefully we're all okay with the cotangent of half a pi is just 0. So think about your values. As you go from 0 to pi over 2, are your good sneeze. Is cotangent positive or negative in this quadrant?
Positive.
It's positive.
Positive.
How about in this quadrant? It's negative. So our graph has to go from positive values to negative values as you go from 0 to pi. So can you visualize what that looks like?
This is the reverse of it.
Exactly, yeah. That's perfect. It's almost like a upside down tangent curve. And the same exact thing happens as you go from pi to 2 pi. Right? You go from positive cotangent values to negative cotangent values. And so this graph, it's a lot like the tangent function. It's just this curve, this weird little curve repeats itself over and over again. Okay? How do we feel? How's your smorgasbord over there?
I'm kind of over it.
Okay. So, all I was going to show you was. You okay, Julia?
Oh, yeah.
Sleepy Julia?
I'm very sleepy.
No. Okay. For all the Twitch fans. Thanks for the 100 bits. Oh man, that's good video production right there. Let's get this far. Oh, oops. Okay. Well, if anyone ever watches this video, you can just pull up Desmos and type this stuff in yourself, and it'll look a lot better. But all I wanted to show you was these functions obey the exact same principles that every other function we've studied obeys. For example, if I put a 2 out here, all the y values get multiplied by 2. So, like I was talking about earlier, okay, this point used to be at pi negative 1, but now it's at pi negative 2 because we multiplied the function by 2. What if I throw a 2 inside here? Scrunchy, scrunchy, right? So now, say this point that's at pi 1, that point used to be over here at 2 pi 1, but since I doubled the x, all my x values got cut in half. Okay? And so you can, if you're feeling at all confused, it's nice to have a tool like this that you can go and kind of visualize what's happening. Okay, as A gets bigger, it's more scrunched up. As A gets smaller, it's less scrunched up, that kind of thing. You can plug in specific values and say, okay, let's say I plug in a 3 right there. Well, now I get this point is 2 pi over 3. This point is 4 pi over 3, and so on and so forth. Okay? Same with the cotangent function, do whatever you like. Cotangent of x, oops. You can put a value in there as well. Scrunchy, scrunchy. And there you go. So if you're doing these problems and you're getting stuck at all, like what happens if there's a pi over 2 in there or a 3, if you're stuck, you can use Desmos to help you out. Okay? How much time do I have?
Like,
Ooh, almost 20. That's what I like to hear. Okay, so that means we can. What you can?
I caught my neck and just like.
Well, it'll be nice if tomorrow I can just cover 2 fairly quick things and be done, and then we can. Tuesday will be just kind of like a work day, I guess. And then Thursday. Kind of forgot the schedule. Friday's the first day of finals, but it's like a half day, right? Don't you do like a half day of school? And then, so. Anyway, tomorrow I'm going to cover the rest of the material. We'll be totally done. So I just want to quickly go over a couple of these wacky dudes here. So let's look at 14 together. And if we do 14 and 16, we'll see what we have time for. Let's look at 14. What do you guys think happens if you put our good friends, the absolute value bars, around a sine function?
They get very sharp.
There's going to be some sharpness. That's correct.
Yes.
See if you can visualize it. Think of the sine function, and now say, well, I got the sine function, and now I'm going to put absolute values around it. So now all the y values will turn positive. Okay? Yeah, you get a really neat function. So if you take this is once again something that you can use a computer to help you out with this if you're stuck. But yeah, this is the sine function. If I put absolute value bars on it, well, this guy, all these points will get transported to above the x-axis because they're all positive now. So your final graph would look something like this. Isn't that neat?
Yo, it's even now.
Oh, man. Good point.
Sheesh, Sean.
Hey. Does the question ask for the... Just says label the important features as appropriate. So as appropriate for this one would be probably indicate this is still 1, the y value. Where are these zeros? Where are these pointies going to be?
2.
Yep, 0. Exactly, same place as this guy, as the original sine function. 0, pi, 2 pi, 3 pi, and so on. Which is interesting. What's the period of this function?
1 pi.
1 pi. Yeah, kind of weird, right? Sine function usually takes 2 pi to complete a period, but since you've taken all those negative parts and made them identical to the positive parts, well, now that one hump is a full cycle. Okay, so then cosine squared. What does something like this look like? This is a little weird, actually. Might surprise you. I like what April said about this one has the zeros on this guy are just the same zeros as the original sine function, right? Would that be true of this one? Bearing in mind that we're all cool with that, right? That's just notationally saying cosine of x squared. So where does this guy equal 0? Where does the cosine function equal 0? 5 over 2, 3 pi over 2, 5 pi over 2, all the half multiples of pi, right? So on and so forth. Okay. This graph is not going to have any what's. True. Yep. What else? It's not going to have any points with negative y values. Right? Because you're squaring all of your numbers. Julia. You're going to make it, Julia. Don't worry. You're going to make it. So then here's, I was looking at those bases. I have my own power ranking, so we can discuss later.
Bases?
The bases.
Oh.
Italy number 1, definitely. And there's this one in Germany that's like really close to, it's on the west side of Germany. Anyway, I forget the name.
There's one in Ireland too.
Huh?
There's like one in Ireland or Scotland.
Really?
Yeah.
So anyway, the biggest is going to be is 1, right? Because the biggest cosine value is 1. 1 squared is 1. So anyway, it's going to hit. Help me out here if you're confused. At pi, it'll hit 1 because the cosine of pi is -1 and -1 squared is 1.
Yep.
And so what you're going to get is this function. Now here's the funny part. Is it pointy? We don't have any good way of proving this, but it turns out it's not pointy.
How do you determine if it's pointing?
What? Well, we can use, for now, I guess I'm just saying take my word for it. But Mr. Desmos can help. If I go cosine of x squared, that's what it looks like. Kind of weird. It looks a lot like just a cosine graph, doesn't it?
Just shifted up.
Yeah, it's actually, I mean, you could actually prove that this is identical. Let's see if I can do it real quick. It's half a cosine function that got crunched up and then shifted up. Isn't that weird? So this is sort of a graphical proof that cosine of x squared is actually identical to half of cosine of 2x plus a half. That's kind of weird, right?
I don't like it.
You don't like it?
No.
Why not?
Satisfying, but I hate it.
It's nice.
Yeah, but I hate it.
Okay. Anyway, so in calculus, when you take calculus, you can get into like, why is this not pointy there? So using something called a derivative, show that the derivative exists. Anyway. Okay, so I want to save the other ones for you. And then 15 is asking you to analyze cosine of x squared. And so the key, or is it sine? It's sine, okay, so sine of x, so for 15, I don't want to give you the answer. It's actually a really interesting question. So this might be too good for him, but so for 15, when you look at sine of x squared, suppose you wanted to really focus on where are the zeros of this function. Where are the zeros? Well, where does the sine function have its zeros? 0, pi, 2 pi, 3 pi, 4 pi, right? So what's the question you have to ask then? When will x squared equal those numbers? So you're going to end up with a set of x values that are like square roots of multiples of pi. And that's just the x-intercepts. And then you have to then reason out, well, between those x-intercepts, what's the function going to do? It's going to, yeah. And if you graph it, what you're going to see is this function that starts making waves, and then the waves get closer and closer and closer together, the bigger x gets. Okay?
That's what you were saying.
Yeah, that was.
All right, let's cover one last thing. Last thing. Which was, yes, good. This is great. This means tomorrow I can just briefly cover the inverse ones, and then we can have a bunch of work time. That'll be neat. Neato burrito. All right. Okay. I think you guys will maybe like these or think they're slightly less miserable than. Okay. Only slightly. So y equals x times the sine of x. You know, be a fun way to do this. I'm just going to show you on the computer, and then this will give you maybe a hint as to why does it look like this. Yeah, that's the real point of this is why. If you take a sine function and you multiply it by x, but to really see, you got to zoom out. This is what it looks like. Yeah, and I'll give you a hint. Why does it look like this? Well, what if I draw y equals x and y equals negative x?
It looks like a fancy bow tie.
I like that better than the other cosine one. I love cosine squared.
Because that's
Okay. So
yeah. The waves are coming through that.
Since nobody said it.
does anyone think they have maybe a short line of reasoning that would be like, why does it get enveloped like that? Yes, AJ.
Because as x gets bigger, the amplitude is also increasing. So yeah.
Yeah, this is kind of like the amplitude, right?
Yeah.
You could think of this dude as like an amplitude function. So yeah, as x gets bigger, so does the amplitude. Right? Is that what you're going to say?
That's around the.
I got another one that's the same kind of idea, but like, for example, if I was making a table of values for this. Don't worry, I'll get to the upshot in a minute. Okay, the upshot's very simple. What are some x values that are interesting? Like 0 gets me 0. How about like pi? What does pi get me if I plug pi in there? If you plug in pi, you get pi times the sine of pi. What's pi times the sine of pi? 0. How about 2 pi? Plug in 2 pi. 2 pi times the sine of 2 pi is 0. So I might go, oh, well, this guy, he appears to have zeros at pi and 2 pi and 3 pi, and that's because that's the zeros of the original function, right? The sine function. Does that make sense? Maybe?
Yep.
But then wait a second. What if I plug in pi over 2 and 3 pi over 2? Well, If you plug in pi over 2, what's the sine of pi over 2? 1. So you'd have pi over 2 times 1, which is pi over 2. Plug in 3 pi over 2, you get negative 3 pi over 2. Now do you see how this x and the y value are the same size, and this x value and this y value are the same size? So what you're going to get now, those points then would live on the lines y equals x. These are not asymptotes. These are envelopes. So what that tells me is that at these midpoints, the graph's actually going to hit the curve y equals x. We feel, does that make any sense?
Yes.
Yes.
So my curve's going to go bouncy, bouncy. Okay, like that. And there's more interesting stuff to think about, which is, hey, did you guys notice when I first graphed this? What kind of function is that? Starts with an E. Even. Yeah. Isn't that funny? Well, that's because you're taking an odd function and multiplying it by an odd function. If you multiply two odd functions, you get an even function. So you get so just try your best to get a decent looking graph. Okay. Last thing I'll share with you today is you might go, oh, okay, it's kind of a neat shape, but does this have like is there an application for this? Yeah, there's a really big one. Let's actually get two birdies with one stone here. Did I give you one that has an exponential decay function?
No, that would be C.
Okay.
I mean, yes, you gave us one, but we haven't done it.
You did what?
You gave us one, but we haven't done it. I thought
What's the function? It's e to the,
Negative.
3e to the negative x cosine of x, where x is greater than 0. Greater than or equal to. Yeah.
okay. So what would this model?
A lot.
Ringing a bell. Okay, so when you ring a bell, something you may or may not be familiar with, like a sound wave, right? A sound wave is, well, it's like a sine wave, cosine wave is just like a beep, right? Any sound you hear could be modeled as a superposition or a sum of different sine waves, okay, of different frequencies and amplitudes. So, but when you ring a bell, like most real sounds, they attenuate, like they decay. Starts off loud, gets quieter. And so like this, in this case, what this is describing is, yeah, so this is an exponential decay function. So this is the envelope. This dude is the envelope, okay? So kind of like this guy was the envelope before. It's going to be up here at 3. We all remember our decay function, hopefully, right? Now remember with these envelopes, you get not only y equals x, but you get y equals negative x. So you're also going to get this dude, the opposite version of the envelope. And then your function's going to oscillate between the positive and negative. Hello, Mr. Osborne. Good afternoon, sir. So at 0, you get 3e to the 0 times cosine of 0, which is 3. And so your curve's going to go whoop-diddy, 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 forever and ever.
No, it's not.
Isn't that neato? And now that might be a little exaggerated. I'll show you on my computer. 3e to the negative x times cosine of x. Now, of course, starting at 0, I'd have to change the scale here. Like go from like, maybe go from like -3 to 3. This is the problem with exponential decay is those crossings are happening, but they just happen, it takes a long time. So if I went like, I'm gonna really change this thing. Well, it's gonna be tough to see, but you can really see it out here. But that's of course saying you're starting at 0. So if you start at 0, I don't know. Does that make sense? It's an exaggerated Y scale, but that's basically what's happening. If you could zoom way in.